This is part 2 of the Unit 9 review. This part deals with gas stoichiometry. Okay, in this problem we have calcium carbonate decomposing, forming calcium oxide and carbon dioxide gas. The first thing we have to do is we have to determine, because that calcium carbonate is a solid and we're dealing with gas laws and it's actually asking for the volume of carbon dioxide, we have to use stoichiometry to convert grams of calcium carbonate into moles of carbon dioxide. So how am I going to do that? Well, let's start with what we know. 6.25 grams of calcium carbonate. Well, how I relate calcium carbonate to the carbon dioxide is their mole ratio. Well, this isn't moles, so I have to convert this to moles. So 1 mole of calcium carbonate has a mass of 100.09 grams. How do I know that? That's just the mass of calcium, 1 carbon, and 3 oxygens. Okay, once I know the moles of calcium carbonate from the balance formula, I can see that for every 1 mole of calcium carbonate, there is 1 mole of carbon dioxide. So moles of calcium carbonate cancels. I now have moles of carbon dioxide. If I multiply and then divide, I end up with 0.0624 moles of CO2. So now I know the moles of CO2. I can apply the ideal gas law to calculate the volume. And so let's see, I know the pressure is 1.05 atmospheres. I do not know the volume, that's what I'm trying to solve for. The number of moles we just calculated, 0.0624 moles. That value for R is 0.082 atmosphere liter per mole Kelvin. And then the temp is 295 Kelvin. Okay, if I divide by 1.05 ATM, atmospheres goes away, moles goes away, Kelvin goes away. I multiply and divide, and my unit left is liters, 1.44 liters. Okay, the first thing we have to do here is balance this formula. In order to balance this, you have to put a 2 in front of the sodium and a 2 in front of the sodium chloride. And so, once again, I'm going to start out with what I know. 4.81 grams of sodium. Well, I have to find out how many moles that is. Well, moles and grams, I always have 1 mole. 1 mole of sodium weighs 22.99 grams from the periodic table. Grams cancel. And now from the balance formula, I know for every 2 moles of sodium, I get 1 mole of chlorine gas, known as chlorine is diatomic. And so if I multiply and divide, I'm going to end up with 0.105 moles of chlorine. All right, now I need to apply this to the ideal gas law. Notice that it's at STP, so standard pressure, we'll just choose atmospheres, 1 atmosphere. The volume I do not know. The number of moles we just solve for, we can use that 0.082 atmosphere liter per mole Kelvin. And then the temp, it's at standard temp, so 273 K. So if I divide both sides by 1 atmosphere, it goes away, atmospheres cancel, moles cancel, Kelvin cancels, multiply and divide the volume, 2.35 liters. Okay, this is very similar to one of the earlier problems. Started with what we know. We have 15.2 grams of calcium carbonate. We have to figure out how many moles that is. Well, we recall that 1 mole of calcium carbonate has a mass of 100.09 grams from the periodic table. Grams cancel. And now I know that for every 1 mole of calcium carbonate, there is 1 mole of carbon dioxide. And so this tells me that there is 0.152 moles of carbon dioxide present. Okay, so now I need to apply this to the ideal gas law. And let's see, it says at STP, so let's just choose 1 atmosphere. And let's see, we do not know the volume. I do know the number of moles. We just solved for that. Moles, gas constant 0.082, atmosphere liter per mole Kelvin, and then temp 273 K. Alright, so if I divide by 1 atmosphere, atmospheres cancel, moles cancel, Kelvin cancels, leaving us with liters, and I go ahead and perform the calculation, 3.40 liters. One thing that wasn't mentioned with this problem, you kind of would have to know it. You would have to know that its temperature and its pressure. Since it's not listed, I guess we're going to have to assume that it's at STP, standard temperature and pressure. And so the first thing we have to find out, well, how many moles is 14.29 liters of a gas if it's at STP? Well, you have to recall the standard molar volume of any gas. 1 mole at STP has a volume of 22.4 liters. So I guess without that STP information, this problem would have been impossible. But we're going to assume that's what it is. So that's going to give me 0.6379 moles of this mystery gas. Well, I know its mass, and I know the number of moles. And if you notice, molar mass is just grams per mole. And so I'm going to take the 45.22 grams and divide it by 0.6379 moles. When you do this, you come up with 70.89 grams per mole. Oops. And then it says, what gas have you found? Well, if you look, chlorine being diatomic, each one weighs 35.45. You take that times 2, it's roughly 70.9. So more than likely it's chlorine. Okay, for this first part of number 30, you have to think back to our solubility unit, and we have to really do a proportion. Okay, so I know that there are 32 milliliters of carbon dioxide that dissolve in 15 milliliters of, let's say, ginger ale. And I want to know how many milliliters of carbon dioxide will dissolve in 275 milliliters of ginger ale. Well, how do we solve this proportion? Cross multiply. So we get 275 milliliters up here. The milliliters of ginger ale cancel. Multiply 275 by 32 divided by 15, and you get, with 2 sig figs, 590 milliliters of CO2. But notice it doesn't ask for how many milliliters, it asks for how many liters. So if you take the 590 and divide by 1,000, you're essentially moving the decimal 3 places to the left. You get 0.590 liters. Now, what we need to do is, it wants to know what the volume would be at STP if these other conditions were met. And so this is a combined gas law problem. Let's see. I know the initial pressure, 0.5 atmospheres. The volume we just solved for, 0.590 liters. And let's see, it said at 365 Kelvin. Okay, and we know, okay, 1 atmosphere. We do not know the volume, but the temp is 273 Kelvin. Cross multiply, the 273 Kelvin comes up here. The 1 atmosphere goes on the bottom. Those go away. Atmospheres cancel. Kelvin cancels. You're left with liters. Multiply and then divide. 0.221 liters.